All right, here we go, the last little bit of probability and stats. This is the normal distribution. So keep in mind we've talked about the binomial distribution. We talked about distribution of a discrete random variable. And so this is another distribution. This is a normal distribution is something that takes on a continuous, it's a continuous variable. So this would mean that any numbers between 16 and 28, 28 and 40 are possible outcomes, etc. And the normal distribution is modeled by a curve, and it is representing area under the curve, which is if area under the curve is what we're talking about, and we're talking about this in terms of probability, the area under any normal curve has to equal 1 because that would represent everything, which would be 100%. And so when we look at pieces of the normal curve, which is what we're going to do, we're looking at little sections of the area that's happening underneath the curve. And I'll explain why that's important in a little bit. The key about normal curves in general, they have the same overall shape. And that overall shape is demonstrated down here in both of these. They are unimodal, so they only have one mode. They are symmetrical, and they are bell-shaped. So sometimes you'll actually hear them referenced as a bell curve, the normal bell curve. So that being said, they don't all look exactly the same. So this is one normal curve right here, this purplish guy right here. And this is a different normal curve, the one I'm tracing in red. They are both unimodal, they're both symmetrical, and they're both bell-shaped, but they're not exactly the same. Now the area underneath the red one is equal to 1. The area under the purple one is equal to 1. Notice that this makes up for it by having more area up here, and the purple one is making up by having a little more area off in the tails. And so any normal curve is described or defined by two values, the mean of that distribution, which is the average, and the standard deviation of the distribution, which is the descriptor of spread or width. So both of these distributions, the purple one and the red one, have the same mean. So you'll notice that they both are centered right at the mean. So that's also going to happen with normal distributions. That mean is going to be dead center. And it will also equal the median. But the standard deviation is going to dictate the width. So this has a standard deviation of 12. The purple one is a little wider, and so it's a little flatter. And the red one has a smaller standard deviation, so it's a little skinnier, but makes it taller. And what that means is that the values on average in the red distribution are a little closer to the mean, and so that's why you get this larger peak. More values are riding close to the average, and the purple one, they're on average, they're farther away from the mean, so they're going to be outside of it a little bit more. So it is called a normal distribution, and a normal curve. It doesn't actually mean normal in the sense that you think it. It's actually a pretty special distribution. It also doesn't mean everything we see is considered a normal distribution. A lot of things like heights and test scores are normally distributed, but everything isn't normally distributed. So things like salaries and home prices, those are not normally distributed, so they wouldn't we wouldn't be able to do some of the calculations we're going to talk about the next class with those distributions. Also, as you go forward in AP Stats or this second portion of this course, a lot of times we don't know if everything is perfectly normal. So a lot of times we'll talk about things being approximately normal, and that's going to be good enough and close enough to be able to use the characteristics we're going to discuss. So try to eyeball where the standard deviation, how far away a standard deviation is in a normal curve, is really where the points of inflection are, and that's going to be kind of a calculus term we talk about later, but it's really where your graph starts to go from being more steep to a little bit less steep, and it is a little bit harder to eyeball in the beginning, and so don't worry about it being perfect, but you should be able to kind of generally ballpark about how far away a deviation is. If I were to give you a normal graph, you could probably mark those off. And again, this is a little hint down here about in the normal distribution, the mean and the standard deviation definitely define it, but most distributions, that's not the case. So it's very special and unique in that regard. So this is talking about the the mean, and we're marking it as 0, meaning that we're not anywhere away from the mean. We're right dead center at the mean. And then this would indicate that I've moved 1 standard deviation to the right, 2 deviations to the right, 3 deviations to the right. And the negatives are to the left, and we're going to talk about those a little bit more in a minute. So this is standard deviations from the mean, and we're going to look at how that helps us in a moment. So in general, we can do this, it's an approximation. Sometimes it's called the empirical rule. Sometimes it has the generic name of the 68, 95, 99.7 rule, and you'll know why that is in a minute. But you can use this as a calculation method if you want. And what it means is that approximately 68% of all observations fall within 1 standard deviation from the mean. So that's just my notation right there, just means standard deviation. That's sigma for standard deviation, lowercase. And so what that tells us, if up here, that if I look at this curve right here, there's 1 deviation to the right and left. Oops, I did not want that guy to move. 1 deviation to the right and left. Notice that means that's about 68% of the overall area of the normal curve. And that means that generally speaking, in a normal distribution, if you go 1 deviation above or 1 deviation from the mean, you'll have captured about 68% of the population of that distribution. So that's quite a bit, which is one of the reasons why it's nice to deal with normal distributions, because you have such a good chunk of people or individuals or items close to the mean. So that takes care of the 68. So guess what? If you move within 2 deviations from the mean, you capture about 95% of the observations. Or in this case, if I went out to here and I colored in from 2 deviations away, notice that as I color that in, that's almost the entire curve. From 2 deviations above to 2 deviations below, I've basically shaded in almost the whole curve. In fact, I've shaded in about 95% of that curve, which means that 95% of the observations in this distribution will be within 2 deviations from the mean. And that takes care of our 95. So that gets us to 99.7, which means that approximately 99.7% of observations fall within 3 standard deviations of the mean. So that would be out here all the way. I'm great at scribbling. Notice that there's just a little bit, teeny amount of space. This is like a horizontal asymptote, but there's not much out here, which means in a normal distribution, there's very few observations, almost none, that are within 3 deviations from the mean. So if we're talking about things like being outliers and those sorts of things, it kind of makes sense that if like being way out here, it would be unusual to be that far away from your mean. So here is a little picture of that, and it might be confusing, and I apologize if it is. That was not my intent, but it helps break it down. So the mean, again, is always in the center, and this is saying I'm going 1 deviation. This is like basically that 1 and -1, and we said that was 68%, so I've broken that into pieces, 34%. And if I go to 2 deviations, I've got 95%. So if I've got 95% from 2 to the left and 2 to the right, if I take 68 away from 95 and split it in half, I'll get 13.5 in each of these little pieces. So this might be a helpful tool to have ready to answer questions when they ask you about your values. So here we go. I'm going to kind of leave this right here. Distribution of women's heights is approximately normal. And again, so this is something I do need to reference. This in AP Stats, if you see this notation, the first number is the mean and the second number is the standard deviation. That's just general notation for normal distribution. I've seen in Cognitive for IB that sometimes this second number is actually the variance. And so I'll be very specific in telling you what this is at this point. But for us, this is going to be the standard deviation. So they want me to sketch this thing. So here we go. Sketch it. This is going to be a little bit sloppy. And I need to mark the mean, which is 64 inches right here. And then I'm going to go about 1 deviation up 2, and 3 to the right, 1, 2, 3 to the left. I want those to be spaced because they each represent the same amount, which is 2.5 inches. So, oops, this is 64.5. So if I go 2.5 inches up, that would be one deviation above average, would put me at 67 inches. And one deviation below would put me at 62 inches. So I added 2.5 and I subtracted 2.5. And then if I add 2.5 more, I will get to 69.5. And if I subtract 2.5 more, I get to 59.5. And if I go one more deviation above average, I'd add 2.5 to this as well, which would get me up to 72. And if I take 2 away from this, I get down to 57. So that's kind of the end markers. There would be some people that were above and below these heights, but basically this is saying that most people are not taller than 72 inches in this distribution, and most people are not shorter than 57 inches. And so if this question is what percent of young women have heights greater than 67, so notice that that is right here, and I want all of this information over here. That's all of it. So there's multiple ways to calculate this. For me, what I would do is if I want to know that, what I know for sure is right here marks 50% or halfway. So I know this side would be half or 50% of the observations. But I also know from this little diagram right here that this chunk, this first little piece here is 34%. So if I know this is 34%, what I could do to figure this out is go, well, half of it minus 34 gets me to 16% as the percentage of people who would be taller than that. You could also just add these pieces up and that would work as well. So now it wants the percent of young women between 62 and 72. So that would be here and here. So notice that that is not including this part out here. So again, I have a couple options. I can add all these up, or I can figure out that this is half, add another 34 and take that little piece away. It doesn't matter. So if I do it that way, again, if I consider this as half, that would be 50%, but I've got to add this extra 34 that's on the left side of it. So that would get me to 84, but I don't want that little piece beyond 72, which is this little bit right here, which isn't much. So I'm not even subtracting a full percentage. I'm subtracting 0.15, so it would be 83.85%. All right, you are going to do something similar with these test scores. This is the Iowa Test of Basic Skills. That's what that stands for. You're going to sketch it, and then you're going to answer these two questions, and I will pause for you. Here is the distribution, and you had the unfortunate job of having to deal with these decimals, adding and subtracting. I apologize for that. To be less than 3.74, as a test score, would just be this little bit over here that keeps going. That would be 2.5%. And the second one between 5.29, which is right here, and 9.94, which is right here, it would be all of this. So you could get that by adding your 68 plus this extra piece right here, which was 13.5 to get 81.5. So there you go. And we are going to, I'm going to end this video because the next thing we're going to do is talk about position in your normal distribution. And we're going to talk about that in terms of how many standard deviations we are away from the mean. And so this will be a second video. Hopefully it won't be as long, and that'll be the way it goes. Okay, ending it.